We are a group of 4 members, which includes Asma Maqsood, Mehrunisa Khalid, Sabeen Mustafa, and Shafaq Mirza. Since last evaluation, we searched for available speech recognition libraries for Android. First, we see Android built-in speech recognition class, which provide access to the speech recognition service that allows access to speech recognizer. All callback methods of this class must be invoked from main thread. But with this class, we are facing a problem that we need a continuous voice recognition for our application. But this API is likely to stream audio to remote servers to perform speech recognition and consume a significant amount of battery and bandwidth. This API uses offline limited dictionary from phone, which doesn't work properly for our app. It shows better results when used online. For using built-in Android class for continuous speech recognition, we use Audio Manager with Speech Recognizer. Because the speech recognizer is not meant to be used as continuous speech recognition. For using speech recognizer class for continuous speech recognition without tapping on mic, for every command we use it with service by using Audio Manager, which records voice, search in system and give all possible results. After showing results, it again starts listening. It doesn't work efficiently for real time use because it takes too much time for computation and works slowly. We also found another library, Artiome.js, but it works mainly for web-based applications. We don't found any material for Android. It needs strong internet connection for efficiently working. We found Google Cloud Speech API, which provides powerful speech recognition. This API powered by machine learning and cover 110 languages. It works efficiently in real time and also accurate in noisy environments. But this API is not free and is priced per 15 seconds of audio processed after a 60-minute free trial. Another library is Bing Speech API by Microsoft Azure. The cloud-based Microsoft Speech API provides developers an easy way to create powerful speech-enabled features in their applications, like voice command control, user dialogue, using natural speech conversation, and speech transcription and dictation. It also works fine for Android applications. You have to sign into Microsoft for getting free trial of 5,000 transactions. Then they give you an API key for 30 days. We try free trial by getting API key and it works very accurately for English US language. Our previous search is based on those APIs from which some APIs don't work properly in real-time scenarios and some APIs are expensive to buy. So we explored some open source speech recognition toolkits, which includes Pocket Phoenix, Carldi, and HTK. Pocket Phoenix. CMU's Phoenix toolkit has a number of packages for different tasks and applications. It's sometimes confusing what to choose. To clean up, here is the list. Pocket Phoenix is recognizer library written in C. Sphenix Train uses acoustic model training tools. Sphenix Base is sport library required by Pocket Phoenix and Sphenix Train. Sphenix 4 is adjustable modifiable recognizer written in Java. Carldi for Android. Carldi is a toolkit for speech recognition written in C++ and licensed under the Apache license. CALDI is intended for use by speech recognition researchers. The training is of high computational expense. Implementation and pipelines are optimized for parallel computing, and the training of DNNs support the usage of GPUs to significantly speed up the processing. Due to language models' internal representation as finite state transducers, CALDI requires the conversion of ARPA language models as trained by the aforementioned tools into a decoder specific binary format. For this purpose, a number of utilities are used, including the tools ARPA2FST, FastCompile, and multiple Perl scripts. HTK. The last one is HTK. The Hidden Markov Model Toolkit is a portable toolkit for building and manipulating hidden Markov models. HTK is in use at hundreds of sites worldwide. HTK associated with large vocabulary decoders, HDecode and Julius. This toolkit provides a good documentation and example of a basic training pipeline. Further development of advanced techniques is possible but requires extensive knowledge and very much time compared to the other toolkits. In most cases, the development of an own customized tool chain from scratch is needed, which make the training a difficult and error-prone task for inexperienced people. Then we see comparison between these three. The time spent to set up, prepare, run, and optimize the toolkits was most for HTK, less Sphinx, and least CALDI. Compared to the other recognizers, the outstanding performance of CALDI can be seen as a revolution in open source speech recognition technology. The toolkit of the Sphinx family also come up with a training tool not containing all techniques of CALDI, leading to less accuracy, but also enabling training and doing speech recognition shortly after installing the system. HTK is the most difficult toolkit. Setting up the system required the development of the training pipeline, which was time consuming and error prone. The results obtained from HTK are similar to Sphinx, but the effort to get these is quite larger. According to research, we found that CALDI providing the most advanced training recipes gives outstanding results out of the box. The Sphinx toolkit also containing recipes and enables good results in short time. HTK provides the least support and requires much more time, knowledge, and effort to obtain results of the order of the other toolkit. After this research, we decided to work on Pocket Sphinx and search some codes for understanding its working. We identified further open source systems and kits, which includes RWTH, HN Automatic Speech Recognition System, Segmental Conditional Random Field Toolkit for Speech Recognition, Improved ATROS, SRI International's Decipher, EDUP's Juicer, Shout Speech Recognition Toolkit. But we did not select any of them for our project because they are not as widespread in the community or as easy available like the chosen one, and therefore restrict the accessibility. After researching on Pocket Sphinx, we found that for accuracy of Pocket Sphinx, we must learn model training from Sphinx train, which depends on language processing. We must learn language processing for better use of this library. HMM algorithm used for language processing, hidden Markov model, is a statistical model in which the system modeled. The acoustic models of Pocket Sphinx and Sphinx 4 are trained with the CMU Sphinx Train Toolkit, providing all necessary tools to make use of the above described features. Scripting is not necessary. All parameters can easily be set in a configuration file, but a certain level of expertise in speech recognition is necessary because the documentation is sufficient but not extensive. Efficiency level is lower than online API. Sometimes it works appropriately, sometimes even not respond on commands. Sphenix uses the CMU language model toolkit. The toolchain contains extracting word frequencies and vocabulary from the input text with text to WFREQ and WFRQ to vocab, followed by generating the ARPA language model file with text to IDNgram and IDNgram to LM. Custom parameters are, for example, the n-gram order, whether open vocabulary is permitted, and the discounting methodology of handling unseen n-grams. The ARPA file has been converted into binary format to speed up decoding. There are two major parts. One is pronunciation evaluation and other part is about deep neural network in Pocket Sphenix. Hopefully the accuracy of decoders will improve significantly. We have to train our library for different accents, languages. In contrast to Pocket Sphenix, Sphenix 4 is limited to continuous acoustic models. The speech recognizer is the main class to access decoder functionality. It is created with the help of a speech recognizer setup builder. A speech recognizer builder allows configuring the main properties as well as other parameters of the decoder. Example, setting acoustic model and dictionary and getting recognizer for listeners. The decoder configuration is a lengthy process that contains I/O operations, so it's recommended to run it inside an async task. Once you set up the decoder and edit all the searches, you can start recognition with recognizer start listening search name. You will get notified on speech end event in the on end of speech callback of the recognizer listener. You could call recognizer.stop or recognizer.cancel. Later we'll cancel the recognition. Formal will cause the final result to be passed in the on result callback. Demo of Pocket Sphenix working. Here is the demo of Pocket Sphenix working. Here we give digits, forecast and fonts commands to show the working of the app. Now Bluetooth detection. Our app needs Bluetooth detector. Bluetooth is a wireless technology standard for exchanging the data over short distances from fixed and mobile devices and building personal area networks. The connection of Bluetooth devices are going through different protocols and a complete step-based process. The Bluetooth detection module connects our app with the user's car and gets the required information about the car stats. Creating a Bluetooth connection between two devices is a multi-step process involving three progressive states: inquiry, paging, and connection. Bluetooth have different modes which includes active mode, sniff mode, hold mode, and park mode. The Bluetooth protocol stack is split into two parts: a controller stack and a host stack. The controller stack is generally implemented in a low-cost silicon device containing the Bluetooth radio and a microprocessor, while the host stack is generally implemented as a part of an operating system or as an installable package on top of an operating system. Controller protocols include only one protocol, that is link layer. It further uses 8 logical protocols named as asynchronous connectionless, synchronous connection oriented, active slave broadcast, Parked slave broadcast, link control protocol, link manager protocol, low energy link layer, host controller interface. Host protocols include different protocols that is logical link control and adaptation protocol, Bluetooth network encapsulation protocol, radio frequency communication, service discovery protocol, telephony control protocol specification, audio video control transport protocol, audio video distribution transport protocol, object exchange, low energy attribute protocol. Using the Bluetooth APIs, a Bluetooth module in our application can perform the following: scan for other Bluetooth devices, query the local Bluetooth adapter, establish RF COM channel, connect to other devices through service discovery, transfer data to and from other devices. We completed the documentation on Bluetooth detection and its protocols, and now start developing our Bluetooth detector module. We further fix some bugs in email module. Here, email without voice commands includes sends email from our app using intent object without any permission from the user. Previously, we tried to code email sending using SMTP, but security violation issue occurs in sending email because it takes user email and password, and user is not comfortable with this. Now by using Gmail, it takes recipient, subject and message body from user manually. It don't use voice yet. When user press compose email, then it switch to the Gmail and user only need to click just one button to send the mail. Here is the demo of email sending using SMTP. Here is the demo of email sending by using Gmail. Message receiving without voice command. For message module, write SMS, read SMS and receive SMS permission is required. Broadcast receiver is used for receiving message. When message received in our app, we will notify a user that message received with sender's phone number and message. List view is used to show all the received messages. Whenever a new message received, this module updates the message list. Here is the demo of message module testing. When message received, it notifies user by showing toast, and when message receives, then message show in the list view. We further worked on the abstract named Impact of Interactive Voice Response based handheld device on driving behavior, assigned by Sir Mubashir. Thank you. Allah Hafiz.